Welcome back everyone. So, in the last lecture we were looking into the response of system, and we found that response of a system when input is equal to 0 is called natural response of the system, and such a response is related to the poles of the system. Today we go ahead from that point and check how will the system behave when we give input to the system. So, when we give input to a system, we call the response of the system or the output of the system to be the force response of the system, considering initial conditions to be 0. So, like in natural response, when you had ut equal to 0, you had initial conditions, some non-zero initial conditions, then solving that is equivalent to solving the homogeneous differential equation. In case of force response, while solving the ODE or the differential equations, we consider the initial conditions to be 0, however, the input is non-zero in this case. So, mathematically solution of the ODE governing the system with initial conditions 0 is what is force response of a system, whereas natural response of a system is the solution of the homogeneous ODE governing the system, where you are considering input to be 0, but initial conditions are non-zero. So, we go back to the example that we took. For example, we had that RLC circuit. Now, notice that we will no longer consider Vt to be 0, and in the similar way we will no longer consider force to be 0. Now, in order to bring this RLC circuit differential equation into a nicer differential equation form where integrations are not involved, we can differentiate this equation, and this is the final differential equation you get. We can consider this to be some function, say a of t. Okay. So, again this equation, differential equation, and then this differential equation, both of them almost have the same form. Then we go back to the same idea, we can represent the differential equation with this form, and so we will find out the first order differential equation. Notice that now the ut terms are no longer 0. So, we are actually following the same procedure, except that ut is no longer 0. We are just going ahead with the with substituting ddt of z1 equal to z2 and z1 equal to z, or z equal to z1. So, this is the differential equation we get. Now, this is the new additional part that you are getting. Initially when we found out natural response, ut was 0. So, this part was no longer present. So, let us try to simulate this system like we did for the natural response case. This is the code. Now, the only thing new here is the input. So, we are defining the input here. You can see what I have done is I am taking a exponential input of the form of this form. This is an exponential input that I am taking. This is your ut. You can take something else also. I am just giving you an example. I am taking this as the input of the system, and for that I am writing down the parameter values here. And on the right hand side here you can see there is no change at all, except that the differential equation now has an extra term, that is because of this extra term that is coming. So, z2 dot has this extra term, except that nothing has changed. So, we have taken into consideration the input now. Initial conditions we are keeping 0 here. So, let us see how does the system behave. So, these are the same code, and you can see this is how the system is behaving. So, you can see that for this system initial there are some oscillations, and then finally it steadies, the output steadies to 0. Okay. So, this is how we can simulate the force response. Now, you see I can always give initial conditions here. Let me give some initial conditions, say 1 0 is the initial condition, and I can run the system. The only thing that is differing is that you see it is starting from 1 now, because Z1 is 1, which is Z. So, only difference is that the initial condition is changing, but the structure or the way the output is changing almost remains the same. So, basically what I am trying to say is that this code that we have written out can be used both to find out natural response, forced response, and together both the natural response and the forced response together. So, actually when you take a system, the actual output of the system is the addition of the natural response and the forced response. That is the actual output. If your initial conditions are 0, then you can get rid of the natural response, because we know that if initial condition is 0, input is 0 for an LTI system, the output will come out to be 0. So, in that case you will only have the forced response. If we go back, so as written here, response of a system is equal to natural response plus forced response, and this has another name which is known as natural response is known as zero input response, because the input is 0 in this case, and forced response is known as zero state response, because the initial conditions or the initial state conditions, I will come to what do you mean by state later on. However, I mean just for now, just remember that this is a variable, internal variable, a variable that defines the system. Okay. So, the initial conditions of those variables are 0. Okay. You can think of it like that, that in the differential equation that you get, the initial boundary conditions, the initial values of the variables in that are 0. Okay. So, response of a system is nothing but natural response plus forced response, in other words 0 input response plus 0 state response. Now, till now we were looking into response from the perspective of inputs and initial conditions. Now, we step back and again look at the response from the time perspective. So, here you can see in this, here you have a diagram where we have a plot. It is similar to what we simulated. So, you can see that initially the response of this system is quite oscillatory, but after some time it dies down almost, and finally it goes to a value of 0. It may go to some other value also, it is just an example. So, in terms of time, in the initial time, the response of the system has a transient behavior, okay, and that part is what is known as the transient response of a system. Now, you can ask, when do I say a system has up to what time does a system has transient response, up to what time does the system has steady state response? That is very difficult to differentiate, but in general when the transients die down, when the oscillations die down, we say that the system is settled to its steady state value. So, I will come to what steady state value soon. So, transient response is the temporary part of the system response that occurs right after an external input or disturbance is applied. That is how transient response is. Whereas, steady state response is the long term behavior, means after some time how is the system behaving, that is what steady state response is. So, when you look at steady state response, the transients must have died down, and then only you can look at the steady state response. Okay. And the value to which the output settles to at steady state is called the steady state value. Mathematically, steady state value is nothing but limit t tends to infinity y of t. So, as t tends to infinity, what is the output? That is called steady state value. So, for example, in this plot you can see the output is settling at 0, right. So, in this plot YSS will be equal to 0. Okay. So, you see limit of t tending to infinity, a function value or a signal's value. This can also be found out with the help of Laplace transform, right. If you remember the final value theorem, we can use the final value theorem to find out limit s tends to 0 s of ys, that also will give you the steady state value. However, remember we had some conditions which should be satisfied, then only you can apply the final value theorem. So, you check those conditions. If the Laplace transform satisfies those conditions, then you can apply this formula and find out the steady state value from directly from the Laplace variable as well, or the Laplace transform of the output as well. So, as a whole, the transient response shows how the system reacts, while the steady state response shows how the system remains once it has stabilized. So, these are very important words that we will need when we will be designing controllers, which is our basic aim in this course actually. So, remember these words: transient response, steady state response, steady state value. These are very important words. So, you should know what these are in the beginning itself. Okay. Now, there is another kind of response. So, see, till now what we have done, we have seen response of a system, defined response of a system based on input and initial condition, natural response and forced response. We have also defined response of a system based on the time scale. So, at the beginning when there are transients, that part is called transient response, or fluctuations, that part is called transient response, and when it steadies, the output steadies or the signal steadies to some value, then we call that the steady state response. Now, there is another thing which is called frequency response. Now, what is frequency response? The frequency response is the steady state response of a system when the system is excited with sinusoidal inputs at different frequencies. Okay. If you have a system, again LTI system, if you have a system, you are giving sinusoidal input to the system with different frequencies, okay, then the output that you get, that is called the response of the system with respect to the frequency which you are giving as input. Okay. So, now for an LTI system, it turns out, LTI system has nice properties, right? It turns out that when you give sin omega t as input to the system, the output frequency remains the same, the frequency do not change. The only change that happens is the magnitude changes to g of j omega magnitude. So, basically whatever transfer function you had, in place of s you put j omega, you will get numerator a complex number, denominator a complex number, you take the magnitude of that, that will come as the magnitude, and the phase will be the angle that you get. So, for example, suppose the system was 1 by s plus 1 and the input that you are giving is sine of t, say, okay, then the output of this system would be, so let me write down yt, output of this system will be equal to g j omega, omega is 1 in this case, sine omega, omega is 1 plus angle of gj. What is the meaning of that? What is gj? Gj is 1 by 1 plus j magnitude sine of t plus angle 1 by 1 plus j. And what is that? That is nothing but 1 by root 2 sine of t plus this will become minus of, so this will become minus of tan inverse of 1 by 1, which is 45 degree. Okay, because why minus? You see, when I am finding the angle of 1 by 1 plus j, this is nothing but tan inverse of the angle of 1. What is the angle of 1? 1 plus j 0. So, j 0 by 1 minus, since 1 by 1 plus j is in the denominator. So, we will have tan inverse j 1, right, 1 by 1. So, tan inverse of 0 is 0 and then minus tan inverse of 1 is 45 degree. So, your final output would be 1 by root 2 sine of t minus pi by 4. Okay, or if you want to write it in the degrees, so t minus 45 degree. So, this will be the output of the system. So, see, in LTI system it is nice, right? I mean the frequency is not changing. Okay. So, you can see this in this circuit. This is an RC circuit. You can see the R here, you have an R here and then you have a C here. So, this is an RC circuit which is grounded, okay, and here we are giving input to the system. So, the input here we have giving some sinusoidal input to the system, okay, and then here we are checking the output. This is the output of the system. Okay. So, let me just get rid of this part. Yes. So, you can see again you have this resistor, you have this capacitor which is grounded, and then we are giving a sinusoidal input here or omega t like this. We are giving a sinusoidal input and the output we are measuring here, okay, the voltage output. So, that is what we are doing. So, this is a simple RC circuit, this is an LTI system. Let us see what happens. So, this is the input given to the system, okay, a sinusoidal input, and now I will start channel 2, and as soon as I start channel 2, which is the output of the system, notice the output of the system. So, notice the output of the system, it is also a sinusoidal signal, however, the magnitude is less, and I see the scales are the same. So, there is no difference in scale. So, the magnitude is lesser than what was the input, and also there is a phase shift, and you can also see that the frequencies are also the same. You see, if you check carefully, this is one full cycle, whereas if you count the similarly here also you will get a full cycle. See, this is the full cycle, right? You count the number of divisions, it will come out to be the same. Okay. So, this is how a system, LTI system behaves when sinusoidal inputs are given. Now, in that case, do not you think that if I tell you what is the frequency and you tell me what is the magnitude of this and the angle this, with these three information I can tell you how the system is behaving at different frequencies, right? And that is why we can visualize the frequency response of a system using two plots. The first plot is called a magnitude plot, where what happens is you take omega in the x axis and in the y axis you plot this. So, for different values of omega you will get different values of magnitude of g j omega, you plot those things, okay. Whereas, for the phase plot you take omega and then you have angle of g omega that you plot. So, this is called phase plot and this one will be called magnitude plot. So, this tells you many things, gives you many information about the system, okay, and we will be using those informations. Now, notice one more thing is that you would like to vary the frequency from 0 to a long variation, so up to megahertz maybe, okay. But think about it, if you want to plot it on a graph paper, will you be able to do that? Because it is a very big range, right, from 0 to 10 to the power of 6, you will not get that many number of points. That is the reason what we do is we use logarithmic scale for the x axis, because as soon as it becomes a logarithmic scale, if 0 is here and 1 is here, this point is nothing but 10 to the power 1. If 2 is here, this point is nothing but 10 to the power of 2. If 3 is here, this point is nothing but 10 to the power of 3 frequency. So, you see, with each division I am increasing, I am multiplying by 10 and going ahead, okay. So, there is a decade jump, that is called. So, these type of plots will be very useful for us, and these plots are what are known as Bode plots, okay. So, we will use these Bode plots quite often, and these Bode plots have many informations. One of the most important application of Bode plot is that if you get the Bode plot of a system, so even if you do not know what the system is, see this thing whatever I have just now said can be done without even knowing the system. Suppose you have a black box, okay, you can keep on giving sinusoidal input to the system where you are changing the frequency, and then at the output you just measure the magnitude of the output and you get the phase change, if you can somehow get that, okay. Once you get that, think about it, you have information about the system, right, for different values of omega. So, what we will do is we can use that information to actually find the transfer function of the system, right. See, we found out transfer function of a system using differential equations. For that you had to know many things about the system, like the physics behind the system. Okay. Now, in the procedure that we will see in the next few lectures will actually help you to find out the transfer function of a system without even knowing the differential equations. Of course, if you know the differential equations, that is like added advantage, but without even knowing that, you can experimentally find out the transfer function of the system using this idea of Bode plots. Okay. So, I will explain about Bode plots in the next lecture. Thank you.